there. Today, from Dartmouth, he's going to talk about the sets of cyclic permutations.
Thank you. So I also want to tell how I met Albert's story. So it was in 2002. This was a meeting in Quebec City, and I was a graduate student back then. And Doron gave this talk that I guess I found it strange because I didn't know him back then. So basically what I remember from the talk is that at the beginning, he spent a long time complaining about how all the other talks at the conference had been so bad because they were using too many slides and they were trying to fit too much information in too little time. And then he gave a talk where basically there was one result he mentioned, and he repeated it several times, and he explained why it was important. And I guess that worked for me because a few weeks later, I had forgotten about all the other talks, but I remembered this particular one, and actually, a lot of my thesis was inspired by that result. So I want to thank you for that. Okay, so what I'll talk about.
So are you going to use one slide?
No, sorry. Unfortunately, this talk will probably have too many slides too. But I tried to shorten it as much as I could. So the talk today is about, it's not about pattern over permutations. That result, by the way, was about fixed points in 3 to 1 and 1 3 to 1 permutations. Yeah. So today I'm going to talk about descent sets. So this is some cute result that I ran across. But before I tell you the main result, I want to tell you a little bit about what was I looking at when I started studying this descent set on cycles. So I was looking at the following problem. So you take infinite words on n letters, and you can think of them as there's a lexicographic order on these infinite words. And then you consider this operation. This is called a shift. So you just take a word and you delete the first letter. And now if you take an infinite word and apply this shift multiple times, you can look at, let's say, the first n shifts of the word and compare them lexicographically and look at what's the smallest one, second smallest one, third smallest one. For example, if you do it for this word here, I mean, a word that starts like this, it doesn't really matter what comes after. This is the word, this is the first shift, the second shift, and so on. Let's say we stop here and now we compare these words. This is the smallest one because it's the only one that starts with a 0. The second smallest one is this one. This is the third smallest one, fourth smallest one, and so on. So then we say that this permutation 4217536 can be realized by using the shift on 3 letters. So 3 letters just means this word only has 3 symbols, 0, 1, and 2. Okay, so it's easy to see that if you limit the number of letters, then you won't be able to realize any permutation. For example, if you only have the binary alphabet, then there are some permutations of length 4 that you won't be able to realize with any binary word. And the question is, if I give you a permutation, what's the minimum number of letters that you need in order to be able to find a word that realizes with those many letters that realizes the permutation? Okay. So I'm going to call that n of pi. So n of pi, where pi is a permutation, is the minimum number of letters that I need to realize pi. So there are some things that are known about this n of pi. So the first one is that if the permutation pi has length n, then n of pi is at most n minus 1. So n minus 1 letters is always enough. And in fact, there are exactly 6 permutations for which you need n minus 1 letters. So that doesn't depend on n, they're always exactly 6. So for example, if you can use 5 letters, well, so if you look at the permutations of length 6, there are exactly these ones that need 5 letters. All the other ones need 4 or fewer. And it's easy to describe how they look like. So basically, you generalize how this looks like. Okay, and then another thing that's known is there's a formula to compute this n of pi that is related to the number of descents of this cycle. So, so what this means is this is the cycle. So I'm taking pi in one line notation. It will be pi in pi sub 1, pi sub 2, pi sub 3. But then I'm not writing it in one line notation, but in I'm writing as if it was a cycle. So some other permutation for cycle notation looks like the one line notation of pi. And this related, I'm going to tell you a little bit more what that means. So I'm going to tell you how to compute n of pi. So if you have pi, you consider this other permutation pi hat, which is a cycle, whose cycle notation is this. And then you replace the entry pi sub 1 with a star. So here's an example. If this is pi, you consider this permutation that's an n cycle. You write it in one line notation, and then this 8 that was pi sub 1, you replace it with a star. So this is pi hat. Now what I do is I compute the descents of pi hat as if, so the way this star works in terms of the descent is you think as if it wasn't there, so you just deleted it. Okay? So there are the number of descents of this is 4, and then this statistic n pi that I was talking about is 1 plus the number of descents of this pi hat. And that's a little bit of a lie, so sometimes you have to add 1 in some cases. But other than that, it's essentially is the number of descents of this transformation of pi. Okay, so this is how I became interested in looking at the distribution of the number of descents on a permutation that looks like a cycle. And well, in this case, it's not just that; it has this little variation where one number has been replaced with a star. But let's not worry about that now, because the result I want to talk about is about descents on cyclic permutations. So here's an example of what I noticed. So these are all the 5 cycles, so there are 4 factorial of them. And each one of them is written in cycle notation and then in one line notation. And then I've put dots where the descents happen. And then I've erased the last entry, pi sub 5. Okay, so if I do that, and now I only look at the descents formed by the first 4 entries, turns out that those descent sets have the same distribution as the descent sets of the 24 permutations of numbers 1 to 3. So what this table is showing is that there's exactly one permutation that doesn't have any descents here, and there's exactly one 5 cycle that doesn't have any descent in the first 4 positions. There are 3 that have a descent in position 1, and there are 3 that have a descent in position 1. There are 5 that have a descent in position 2, same here, and so on. And what I'm going to talk about today is a bijection that proves this, that the descent sets here is the same set as the descent sets here. Now, when I first noted this, and I checked that it seemed to be true for the first 3 values of n, I thought this should be easy to prove because, after all, there's so much preserved. It's the whole descent set, not just the number of descents. Then it seems like you cannot move the permutation that much. So, maybe you just decrease some entries by 1 or something like that. But that doesn't seem to work, and I haven't found any easy transformation like that works. So the bijection is a little bit complicated. There may be an easier one, but I haven't found it. Okay, so this is the theorem. So there's a bijection between cycles of length n plus 1 and permutations of length n, such that the descent set of the first n entries is preserved. Okay, so I guess I'll have to leave, but if it was here, I'd say that there's also a way to prove this theorem non-bijectively. So I found this afterwards. First, I asked him if he knew how to prove this, or if he had heard this. He said no. And then it turns out that from he has a paper with Reutenauer that using some of his ideas, like transformations between permutations and necklaces,